In this lecture, we continue our discussion on the shortest path problem. We have already described the shortest path problem, the Dijkstra's algorithm, and the optimality of the Dijkstra's algorithm in earlier lectures. We have also looked at the cases where theCij's could be even less than 0. Ordinarily, in the Dijkstra's algorithm, theCij's are greater than or equal to 0 as shown in this example, but there could be cases where we could have negative costs also. We also saw how the Dijkstra's algorithm will have to be modified to handle negative costs and how the algorithm is capable of identifying a negative length cycle. Today, we will look at two more aspects of the shortest path problem. The first is what is called successive shortest path, and the second is constrained shortest path. First, let us look at the successive shortest path problem. Let us go back to the same network and example which we have been using to understand the shortest path problem. We already know for this example that the shortest path is 1, 2, 5, 7 with z equal to 50. 1 to 2, 2 to 5, 5 to 7 is the shortest path with 15 plus 25 40, 40 plus 10 50 as the length of the shortest path. Now, what do we do in this successive shortest path? The question that we ask is, this is obviously the shortest path or called as a first shortest path. In this example, we have only a unique shortest path, so there is only one first shortest path. Now, the question is, what is the second shortest path? Is there a second shortest path? If so, what is the second shortest path? And after we answer the question, what is the third shortest path, and so on. So, let us try to find out the second shortest path in this network. So, in order to find out the second shortest path in this network, what we do is we take the first shortest path, which is 1, 2, 5, 7, and we observe that there are 3 edges in this shortest path, 1 to 2, 2 to 5 and 5 to 7. So, we solve 3 shortest path problems. Problem we may call problem P1 with C12 equal to infinity. That is, if we take out the edge 1 2, or if we assume that the edge weight becomes infinity from 15, then we are effectively excluding 1 2 from the shortest path. So, we would solve problem P1 by excluding this from the shortest path, or indirectly putting the value equal to infinity, so that this does not lie in the solution. The second problem will be P2, where we keep this as 15 and then we put C25 is equal to infinity. And then we take the third case where we look at P3, where we put C57 is equal to infinity. Now, we have to solve 3 shortest path problems. So, if we look at the case where C12 is equal to infinity, which means we change this to infinity and apply one pass of the Dijkstra's algorithm, then for the problem P1 we will get the solution as 1367 with z equal to 60. That is, if we make this as infinity from 15, then the shortest path will now involve 1 to 3, 3 to 6, 6 to 7 with z equal to 60. Now, we now solve problem P2 by keeping this as 15 and by changing this to infinity, so that the solution to problem P2 or the shortest path to this problem, where this is kept as 15, this becomes infinity, is now given by 1, 2, 4, 5, 7 with z equal to 55. So, 1 to 2, 2 to 4, 4 to 5 and 5 to 7 with z equal to 55. So, you observe that in this problem P2 we have forced this value C25 to infinity, which is given here, and therefore, the edge or arc 25 does not lie in the solution. We now solve the third problem, which is P3 that we keep here, and for P3 what we do is we retain this to its original value of 25 and we change this from 10 to infinity, so that we do not have this arc now in the shortest path. So, we have excluded this from the shortest path. So, we solve this new shortest path problem again, where these two values regain their original values and this is changed from the original value of 10 to infinity. Now, one more pass of the Dijkstra's algorithm would give us the solution 1 to 2, 2 to 4, 4 to 7 with z equal to 55. So, 15 plus 10, 25 plus 30, z equal to 55. So, now what we have done is this is the first shortest path, 1, 2, 5, 7 with z equal to 50. In order to get the second shortest path, we have created 3 more problems, because there are 3 arcs in this shortest path. So, we have created 3 more problems and each one of them we restrict it to infinity. We take it out of the shortest path and apply one pass of the Dijkstra's algorithm. So, we have got P1, P2 and P3. Now, out of these three, the one that has the smallest distance is the second shortest path. So, in our example, either this or this can be shown as the second shortest path. So, we may now say that this is the second shortest path. We could have said also this as the second shortest path. So, we have now found out the second shortest path on this network. Now, how do we find the third shortest path? Now, in order to find the third shortest path, particularly for this example, since at this point we have 2 solutions with z equal to 55, this automatically qualifies to be the third shortest path, where the third shortest path and the second shortest path in this instance have the same value of 55. So, we may say that this is the third shortest path with 55. We may also say, for example, that we have 2 second shortest paths both with 55, and therefore, we would be interested in the third shortest path, which has a value strictly greater than 55. Once again, in this instance, we have a solution with 60, which happens to be 1 out of the 3, and the way these numbers are given in this network, the minimum number being 10, this would automatically qualify to be the third shortest path. If we wish to say that the third shortest path should have a value distinctly higher than that of the second shortest path. If we qualify this to be the third shortest path with the same value 55, then this automatically becomes the fourth shortest path with value equal to 60. One should bear in mind that the 3 sub problems that we created only in this example have automatically qualified to become second, third and fourth shortest paths respectively. On the other hand, the methodology would actually be slightly different from what I have described. Whatever I have said is clearly applicable for this particular instance or illustration of the problem. In general, the algorithm would run like this. Take the first shortest path. Now, find out the number of edges in the first shortest path. In this example, there are 3. Create 3 problems as shown here P1, P2 and P3 with the respective cost values set to infinity and get the solution for P1, P2 and P3. The smallest among them will automatically qualify to be the second shortest path, say this. Keep the other two in the solution. So, retain the solution, which is retain 1247 with 55 and retain 1367 with 60. Now, in order to find the third shortest path, now take the second shortest path and then set 1, 2, 3, there are 4 arcs in the second shortest path, set each one of them to infinity. Remember that this already has C25 set to infinity because this comes from this path. So, we will now do 4 more shortest paths where the first one will have C25 equal to infinity and C12 equal to infinity. Second one will have C25 equal to infinity, C24 equal to infinity and so on. So, there will be plus 4 solutions coming out of these 4 arcs that we have looked at. So, there are 4 more solutions. So, effectively there will be 6 solutions, some of which may even repeat. So, out of these 6 solutions, find out that solution which has the least value, and in this case it will turn out to be that 55. So, this will become the third shortest path and so on. So, like this we can get the second, third, fourth or any successive kth shortest path for a given problem. The only thing that we have to bear in mind is as we move along, for example, when in this example when we did the first shortest path, we had one pass of the Dijkstra's algorithm. When we did the second shortest path, we have as many passes as the number of edges that are here, and therefore, with every successive shortest path that we wish to compute, we end up computing more and more of shortest paths using the Dijkstra's algorithm. So, the point that I am trying to make here is that the complexity of the algorithm will increase if we wish to use this algorithm to find out successive shortest paths. Nevertheless, this provides us with a certain framework with which we can get or identify successive shortest paths in the network. Now, we get into the other question of why should we study successive shortest paths in the network. Now, the answer to that comes from something like this. So far in the shortest path problems that we have looked at, every arc has one associated weight which I described as either a cost of moving from I to j, or the distance to move from I to j, or the time taken to move from I to j. Now, there can be situations and scenarios where we may define this with 2 parameters. It could mean the cost, it could mean the time. So, if each of these is now described on the basis of 2 parameters, which would be cost and time, then the question is, we find out the least cost shortest path, we could find out the least time shortest path. In some situations we will have where we want the least cost shortest path subject to a condition that the total time taken should be less than or equal to something, in which case the problem becomes a constrained shortest path problem, where we do a cost minimization objective with an explicit constraint that the time taken should be less than or equal to something. We will look at this problem. We will also understand that this problem is actually difficult to solve, but one of the reasons why successive shortest path is useful is that if it turns out that the first shortest path violates the time constraint while the second shortest path satisfies the time constraint, then we might say that the second shortest path is actually optimal to the constraint problem. So, successive shortest path is one of the ways of trying to solve a constrained shortest path problem, particularly when we have more than one parameter that is describing the arc weight. The other reason why we do successive shortest paths is also to get a feel of perhaps the opportunity loss if we do not choose the first shortest path and instead choose the second shortest path. Now we move from successive shortest path to studying the constrained shortest path, and we take a different example to explain the constrained shortest path. Now let us look at this example and let us try to first find out the shortest path, assuming that each of these is a cost of moving from I to j. So one pass of the Dijkstra's algorithm would give us a 0 here. So this would be 8, this would be 6, 6 plus 7 13, 8 plus 9 17, so we will have 13, we have 8 plus 5 13, 13 plus 7 20, 6 plus 3 9. So one pass of the Dijkstra's algorithm would give us the shortest path, which is 1 to 3, 3 to 5 with z equal to 9. Now let us add one more parameter to this, and let us say, that is, say we do put this as 8 comma 3, 6 comma 4, 9 comma 2, 7 comma 4, 3 comma 6, 7 comma 3 and 5 comma 4. Now let us say that the second one that we have added actually represents time to move from I to j. Let us say this is the cost, and let us say this is the time to move from I to j. Now let us also have a restriction, and let us first find out the time associated with the shortest path. Now the shortest path is 1 to 3, 3 to 5, and right now we have the time associated is equal to 10. Now if we have a constraint that this time should be less than or equal to 9, is less than or equal to 9, then what happens to the problem? Now what happens is, clearly the shortest path 1 to 3, 3 to 5 is now infeasible if we add an additional constraint that total time t taken, which is Tij Xij, should be less than or equal to 9. Now how do we solve this problem? So this problem becomes a constrained shortest path problem. So let us first formulate the constrained shortest path problem and then try to see a way by which we solve this. Now the constrained shortest path problem will look like this. Now this will be to minimize sigma Cij Xij subject to the shortest path constraints . Remember that we will have 5 constraints corresponding to these 5 nodes and 7 variables. So there are 7 variables and 5 constraints, and these 5 constraints will be x12 plus x13 equal to 1, minus x12 plus x24 plus x25 equal to 0, minus x13 plus x34 plus x35 equal to 0, minus x24 plus x minus x34 plus x45 equal to 0, and it will be minus x25 minus x35 minus x45 equal to minus 1, and we have this constraint sigma Tij Xij less than or equal to 9. Now xi or xj equal to 0 1. Now this is the formulation of the constrained shortest path problem corresponding to this example. Now xj is now a binary variable. So this problem becomes a 0-1 integer programming problem. Earlier we have seen that the unconstrained shortest path problem, that is, if we leave out this constraint, it becomes the normal shortest path problem. We have already shown that the normal shortest path problem has a unimodular matrix, and therefore we can ignore this 0-1 and solve as a linear programming problem and get solutions that have 0 value or 1 value for the variable. Now first of all, we need to verify whether the unimodularity property is retained with the addition of the constraint. So in order to do that, let us first solve this as a linear programming problem and then see how the solution looks like. So right now I am not going to take you through the simplex iterations, but I am just going to give you the solution corresponding to this linear programming problem, and that solution turns out to be x1 equal to 1 by 3 or 0.333, x2 equal to 0.666, x5 equal to 0.333, x7 equal to 0.666, and z is equal to 10.333. Now x1 is nothing but x12 for our example, and x2 is nothing but x13 in our example, x5 is x25, x7 is x35. So the solution to the linear programming problem is actually arc x12 equal to 0.333, this is 0.666, this is 0.666, this is 0.333, total is equal to, you can see that it satisfies all these constraints plus it satisfies this constraint, it gives us z equal to 10.333. Now clearly with the addition of this constraint, this problem has lost its unimodularity characteristic. If it had not lost its unimodularity property, then it would have given us a solution which is 0-1 valued, which it did not do. So the addition of this constraint takes away the unimodularity property. Therefore it is now not possible to solve this using linear programming or linear programming based technique or a direct implementation of the Dijkstra's algorithm. So we need to do something more. Now what we do in this case is something quite interesting. We have already learned earlier the method of Lagrangian multipliers, where we could take a constraint into the objective function and then do the optimization after we dualize this constraint or take this constraint into the objective function. Now we are going to try and apply that technique here. So what we do is we are going to introduce a Lagrangian multiplier called lambda, which is a Lagrangian multiplier. It's a Lagrangian multiplier. So we take this into the objective function. So we get, so this will become plus lambda times sigma Tij Xij minus t. So we remove this and take this into the objective function by using a Lagrangian multiplier, where lambda is the Lagrangian multiplier. Now Tij Xij is this constraint. Now t is equal to 9 in this example. We have said that the right hand side value should be less than or equal to 9. So we have got this into the objective function. Now if we now look at the constraints, we now go back to the normal shortest path constraints, and therefore this part is unimodular. The only difficulty is that we know this t, we know all these Tij's, but we do not know this lambda. Lambda is another variable that we have introduced into the problem. It is like a dual variable associated with this constraint that we actually relaxed. So this method is called Lagrangian relaxation, and we describe it further. What we can do is that for given values of lambda, it is now possible to solve a new shortest path problem every time. For example, if we look at lambda equal to 1, if we fix lambda equal to 1, then what happens to this? Now this becomes Cij plus lambda Tij. So this becomes 8 plus 3, which is 11. I am just showing it in a circle. This becomes 5 plus 4, which is 9. This becomes 9 plus 2, 11, because this is Cij plus lambda Tij. Cij is 8, lambda is 1, Tij is 3. So it becomes 8 plus 3, 11, 9 plus 2, 11, 6 plus 4, 10, 7 plus 4, 11, 3 plus 6, 9, and 7 plus 3, which is 10. So if we now solve this for lambda equal to 1, we would get a shortest path, we would get a solution with z or it is called L equal to 19. Now what happens? If we solve this for lambda equal to 1, you get this path is 11 plus 9, 20, this path is 10 plus 9, 19. So this path will come into the solution. So 1 to 3, 3 to 5 with L equal to 19. L is the value of the objective function. But we need to do one more thing, which is what we have got as 19 is the value of Cij Xij plus lambda times Tij Xij. But then the full objective function is minus lambda t. So this has to, we have to subtract this lambda t from 19. So this becomes 19 minus lambda t, which will be 10. 19 minus 9, lambda is 1, capital T is 9. So 19 minus 9, which is 10. So when we put lambda equal to 1 and solve, the value L will become 19 minus lambda t, which is equal to 10. Now if you also see carefully, the value here is 10.333, while the value here is 10. Now let us try and solve for some values of lambda. So when we get lambda equal to 2, we got a solution with L equal to 27 minus lambda t, which is 27 minus 18, which is 9. So when lambda equal to 2, it means this value would become 8 plus 6, 14, and so on. So when lambda equal to 2, we effectively got 27, but 27 minus lambda t is 27 minus 18, which is 9. So what we can do is, for various lambdas, we can actually try and get some value for this L, which is the value minus lambda t. Now it's possible to show that for every value of lambda, this value that we get here is actually a lower bound to z star, where z star is the objective function value of the constrained shortest path problem. This is the LP relaxation of the constrained shortest path problem. So this is ZLP star, which is an LP relaxation of the constrained shortest path problem. So we also know that this is less than or equal to z star, where z star is the ZIP star, where the constrained shortest path problem is an integer programming problem. So this is also less than or equal to ZIP star. Now this, any one of these L, or effectively L minus lambda t, is less than or equal to ZIP star. So whatever we observe here by solving this shortest path problem for various values of lambda, every one of them is actually a lower bound to ZIP star. So automatically what we would like to do is to see whether what is the highest value that we can get here, so that we can make the lower bound better and better. Now though we can do this for various values of lambda and show whichever is the highest, so let us just try for lambda equal to 4 by 3, we would actually get L is equal to, for lambda equal to 4 by 3, we would get L is equal to 10.33, which is 67 by 3 minus 12, which is 36. So for L is equal to 4 by 3, we would get 67 by 3. So L is equal to 67 by 3 minus 4 by 3 into 9. So, this is 67 minus 36 by 3, which is 31 by 3, which is 10.333. So, for lambda equal to 4 by 3, we would get a value which is 10.333. We tried with various lambdas, but then it is possible to show that you cannot go beyond 10.333 in this example. Now, if we look at this, when we put an additional constraint that Tij, Xij is less than or equal to 9 in this problem. So, right now let me remove all these. These are specific values for lambda equal to 1. So, I am removing all these values. For this, if we put an additional restriction that Tij, Xij is less than or equal to 9, then we know that there is a solution with 1, 2, 5 with z equal to 13 and time equal to 7. Now, this is actually this is the optimal solution to the problem. Now, we can now realize that every one of these values is a lower bound to this 13. The 10.33 that we got here is also a lower bound to this 13. So, for every lambda that we can try here, we can actually get the lower bound to this 13, and we wish to find out a lambda which would try to get as large a value here, so that this lower bound is tighter and close to this 13. We also know that LP relaxation is a lower bound. So, 10.333 is also a lower bound to this 13. So, now why are we using this? Now, we are using this method for two reasons. One is we wish to know if is there a possibility that the lower bound obtained using these relaxations is actually better than 10.333. If so, then this method can give us a better lower bound than what LP relaxation can give. Now, there are situations where Lagrangian relaxation can give a better lower bound than LP relaxation, but for the example that we have looked at, which is a single constrained shortest path problem. So, whenever you have a single constrained problem and you relax it, it is always possible to show that the Lagrangian lower bound will only be as good as the LP lower bound. So, in this case it is not surprising that both the LP lower bound and the Lagrangian lower bound gave us 10.33. In fact, there is a very interesting way to get the corresponding lambda. Actually, we can even show that if we solve the LP problem and we realize that Tij, Xij is exactly equal to 9. So, the dual variable corresponding to this constraint would have a value of 4 by 3, which is exactly the value of lambda for which we get the best value of the lower bound. Now, this is also fairly clear because we said we took this constraint, we dualized this constraint and took it into the objective function. So, there is something to do with the dual value associated with this constraint. So, for a single constraint shortest path, one can only go as far as saying that the Lagrangian relaxation will only give a bound which is as good as the LP relaxation. But nevertheless, for other problems which are available in the literature, one can show that Lagrangian relaxation can give better bounds than LP relaxation, and therefore, this technique is used to get better bounds than LP relaxation. Now, what is the next thing? Now, the next question that we might ask is, each one of these implies or involves solving a shortest path problem. So, the question is, when I keep solving so many shortest path problems, how do I get the best value of lambda? One of which I said is, this is, so you solve the LP, you know the dual, and then you use it, you will get this. But then it is like, if I do this and I know that by putting the dual I can only get up to 10.333, then the question that comes is, why should we follow that approach? Is there a more structured approach to get the best value of lambda? Now, there are approaches which are, one of which is called subgradient optimization, which is used extensively, but we are not going to cover subgradient optimization in this lecture series. So, right now we would say that we would try and get the best value of lambda either by trial and error or by a structured procedure such as subgradient optimization. We also know that because it is a single constraint shortest path, the Lagrangian relaxation can only be as good as the LP relaxation. But as I mentioned, there are other problems where the Lagrangian relaxation can give a better lower bound than the LP relaxation. Now that leads us to the next question, can the Lagrangian relaxation give us the optimal solution? Now there are times Lagrangian relaxation can give the optimal solution, though it is not guaranteed that for every instance it is capable of giving the optimal solution. For example, even when we put t equal to 9, we realized that Lagrangian relaxation is only going up to 10.333 and it is not giving us 13. So in this instance, this method is only able to give us a lower bound. But on the other hand, if we had put t equal to 7 instead of t equal to 19, if we had put t equal to 7, which means we have changed this constraint to 7, if we did that, then for lambda equal to 4 by 3, you realize that L is actually 67 by 3 minus 4 by 3 into 7, which is 67 minus 28 by 3, which is 39 by 3, which is equal to 13. Now when capital T equal to 7 and if we solved for lambda equal to 4 by 3, we would have got L is equal to 13. Now this is a separate case. So we get L equal, but we also know from here that for the value of L equal to 13, we have a feasible solution with Z equal to 13. We would have got the same 1 to 2, 2 to 5 here as the shortest path with Z equal to 13. So here you have a situation where the Lagrangian lower bound is 13, there is a feasible solution to the problem with 13 and therefore this 13 is optimal. So there are situations where the Lagrangian relaxation technique can give the optimal solution, but most of the situations it ends up giving a lower bound. And for many problems it is possible to show that the lower bound obtained using the Lagrangian relaxation would be better than the lower bound obtained using the LP relaxation, though for the particular example that we have taken, the LP relaxation and the Lagrangian relaxation give us the same bound. So this kind of brings us to the end of the discussion on the constrained shortest path problem. So what we have seen today is we have first seen the successive shortest path problem and then we have seen the constrained shortest path. Now with this background, let us approach the successive shortest path. Now one of the ways of doing it is to go back to this, now find out the first shortest path, then find out the second, third successive shortest path, and the first of those which actually satisfies that constraint will be the optimal solution. So that also brings us it brings us a relationship between the successive shortest path and the constrained shortest path problems. I am not trying to suggest here that a single constraint problem should be solved using successive shortest path, it is not so, but then if we do a successive shortest path on this problem and apply the additional constraint to each one of these paths, it is also possible to get to the optimal solution to the constrained shortest path. So the thing that we understand is both successive shortest path and constrained shortest paths are computationally more intensive than finding the first shortest path. Now successive shortest path involves computing many shortest paths, we do not know how many, that number can be very large, but we may end up computing many shortest paths. Therefore this would be a computationally intensive algorithm. We had already seen that first shortest path we got 1, to get the second shortest path we calculated 3 more, in principle to get the third shortest path you have to calculate 4 more and so on. So the number goes up. Similarly with the constrained shortest path, what we did was we saw that the constrained shortest path problem immediately loses its unimodularity characteristic, therefore it has to be solved as an IP integer programming than as a linear programming problem. So one of the methods we saw was to dualize the constraint such that the resultant constraint retains its unimodularity characteristic, and then once you dualize it you introduce another variable which is the Lagrangian multiplier, and then for different values of this multiplier lambda we tried to get to the solution. And we also saw that in many instances this can only give a lower bound and not the optimal solution, and many times such a lower bound could be better than the lower bound obtained by LP relaxation, though in some very simple instances Lagrangian relaxation is capable of showing the optimum or identifying the optimum for the t equal to 7 case. So, this actually brings us to the end of the discussion on the shortest path problem. So far what we have seen is the basic introduction to the shortest path problem, solving the shortest path using the Dijkstra's algorithm, understanding that the Dijkstra's algorithm is optimal by means of an LP formulation, dual complementary slackness, and then modifying the Dijkstra's algorithm or looking at new algorithms, particularly when theCij's were or could be negative, which means we looked at shortest path with arbitrary costs, and then we also showed how a negative cycle can be identified if there is one, and then we moved into two other problems in shortest path, which are successive shortest path problems and constrained shortest path problems. Now we move to the next of the network models, which is the maximum flow problem. Let us look at this problem for the maximum flow. Now let us describe the maximum flow problem. Now the maximum flow problem is like this. You are given a network. Now this is a network which has 7 nodes, it has 11 arcs, and each network has a weight. Now this weight represents what is called the capacity of this network. Now we are going to assume that there is a source and there is a destination is called the sink in the maximum flow problem terminology. So this is called a sink and this is called the source. Now we are going to assume that a lot of material or fluid or liquid is available in the source and it has to be pushed to the sink. Now if we try to transport or send this from the source to the sink through this network, each of these edges or arcs represents a certain capacity. For example, if we want to send something in this 1 to 3, we realize that you cannot send more than 40 units from 1 to 3. It is like the quantity that it can handle, it is like a discharge, it is like a quantity that it can handle. Similarly, if you choose to use 1 to 2, then it cannot handle more than 40 and so on. So given this network with weights, please remember that these weights are not costs. In the shortest path problem, they represented costs. In the maximum flow problem, the weight would represent a capacity. So given the network with the arcs, with the arc capacities, the problem is what is the maximum flow that I can have from the source to the sink. Also remember that a large amount is available here, or an infinite amount of whatever we are trying to push is available here. So what is the maximum flow in this network? Now let us first apply a very rudimentary algorithm to try and understand the maximum flow and the idea of the maximum flow. Now if we want to send something from 1 to 7, one of the easiest things to do is to identify a path and then try to send something in that path. Now there are several paths from 1 to 7. For example, 1 to 2, 2 to 5, 5 to 7 is a path. 1 to 2, 2 to 4, 4 to 5, 5 to 7 is a path. 1 to 3, 3 to 4, 4 to 5, 5 to 7 is another path, and so on. So, we could identify a path and then try and send something through that path. Now, there are several paths and we could pick the paths in any order that we wish to choose. So, let us try an arbitrary order of choice of paths and see how much we can send through this. So, let us first try and look at a path 1, 2, 4, 5, 7. Now, 1 to 2, 2 to 4, 4 to 5 and 5 to 7. This has a capacity of 40, this has 10, this has 20, this has 30. So, what we can send through that path is the minimum of the available capacities. So, there is a 40 capacity available here, there is 10, there is 20, there is 30. So, 1 to 2, 2 to 4, 4 to 5, 5 to 7, we will be able to send the minimum of them. So, I would say flow equal to 10. Now, what I am doing here is I am going to put a 10 here, saying that I have sent a flow of 10 in this. So, there is a flow of 10 from here, it goes like this and it reaches 7. Now, let us look at another path that we have and let us look at 1, 2, 5, 7. Now, one other thing that we ensure is that whenever we take a path, we try to exhaust the path. For example, when we took 1 to 2, 2 to 4, 4 to 5, 5 to 7, the maximum that we could send was the minimum of the capacities, which turned out to be 10, and therefore, we decided to send 10. We did not send 9 or 8 or anything like that. So, whatever maximum flow that is possible, we try to send that flow, which is equal to 10. Now, if we look at 1 to 2, 2 to 5, 5 to 7, now 1 to 2, the actual capacity was 40, we have already used up 10, so available capacity is 30. Here the actual capacity is 10, the available capacity is also 10. Here the actual capacity is 30, the available capacity is 20. So, we look at 30, 10 and 20, the minimum is 10. So, we put flow equal to 10. So, this gets updated to 20, this gets updated to 10, this also gets updated to 20. Now, let us look at a third, let us look at 1 to 2, 2 to 4 and 4 to 7. Now, we look at 1 to 2, 2 to 4, 4 to 7. Now, 1 to 2, the available capacity is 20, 2 to 4 there is no available capacity, this has been exhausted. Now, 4 to 7 available capacity is 10. So, we will not be able to send anything using 1 to 2, 2 to 4, 4 to 7. We then look at 1 to 2, 1, 2, 4, 6, 7. So, we look at 1, 2, 4, 6, 7, and once again you realize that 1 to 2 available capacity is 20, here it is 0, here it is 10, here it is 20, we will not be able to send much. So, we leave out this. Then we move to 1 to 3, 3 to 4, 4 to 5 and 5 to 7. So, 1 to 3, 3 to 4, 4 to 5, 5 to 7. 1 to 3, 40, 3 to 4, 15, 4 to 5, 10, 5 to 7, 10, because here 20 minus 10, 10 is available, 30 minus 20, 10 is available. So, 40, 15, 10 and 10, we get 10 as the flow. So, you get flow equal to 10, and you now update the flow. So, here this becomes 10, this becomes 10, this becomes 20 and this becomes 30. Now, we look at 1, 3, 4, 6, 7. So, we look at 1, 3, 4, 6, 7. Now, here the capacity, the available capacity is 30, it is 5, it is 10, it is 20. So, the minimum is 5. So, you have flow equal to 5 and we update it. So, you get 15, you get 15, you get 5, you get 5. Now, the last one that we will look at is 1 to 3, 3 to 6, We could do 1, 3, 4, 7 which is also available, but this is 25, this is 0, this is 10. So, we cannot send anything through 1, 3, 4, 7. So, we look at 1, 3, 6, 7. So, this will give us 1, 3, 6, 7. So, this gives us a balance of 15, this is 20 and this is 15. So, we have another 15 that can be sent. So, this is 40 minus 15, 25 is possible, 20 is possible, 20 minus 5, 15 is possible. So, we have sent another 15. So, this gets updated to 30, this gets updated to 15, this gets updated to 20. So, let us see if we have any more paths with which we can send. So, 1, 2, 5, 7, this is exhausted. So, you cannot send. 1, 2, 4, 5, 7 is exhausted, 1, 2, 4, 7 is exhausted, 1, 2, 4, 6, 7 is also exhausted, 1, 3, 4, 5, 7 is exhausted, 1, 3, 4, 7 is exhausted, 1, 3, 4, 6, 7 is exhausted and 1, 3, 6, 7 is also exhausted. So, we now realize that we have a total flow of 30, 35 plus 15, 50 that we are able to send through this particular order or choice of the paths. Now, let us try doing this with a different configuration of or order of these. Now, let us find out a different order in which we send. So, let us first look at 1 to 3, 3 to 6 and 6 to 7. Now, this is 40, this is 20, this is 20, 40, 20 and 20. So, we can send flow equal to 20. So, we update it with 20, 20 and 20. Now, let us look at 1, 2, 5, 7. So, this is 40, this is 10, this is 30. So, we get flow equal to 10. So, this becomes 10, this becomes 10, this also becomes 10. So, let us look at 1, 2, 4, 7. So, this is 30, this is 10, this is 10. So, 1, 2, 4, 7 is another 10, 30, 10 and 10. So, this becomes 20, this becomes 10, this becomes 10. Now, if we look at 1, 3, 4, 5, 7. So, this is 20, this is 15, this is 20, another 20. So, minimum is 15. So, we will be able to do 15 here. So, we get this becomes 35, this becomes 35, this becomes 15, this becomes 15, this becomes 25. Now, let us see whether we have exhausted all the paths. 1, 2, 5, 7 is exhausted, 1, 2, 4, 5, 7 is exhausted, 1, 2, 4, 7 is exhausted, 1, 2, 4, 6, 7 is exhausted because this is complete, 1, 3, 4, 5, 7 is exhausted here, 1, 3, 4, 7 is exhausted, 1, 3, 6, 7 is exhausted, 1, 3, 4, 6, 7 is also exhausted. So, we have exhausted all of them, but now we realize that we could have flow equal to 55 units in this case. So, what have we tried to learn? One is we said that it is possible to increase the flow by identifying a path, and if there is capacity in that path, then we can increase the flow. What we also did consistently was that out of all the capacities that are available, we picked the maximum capacity or maximum flow possible, which is a minimum of the capacities that are available. And then we exhaustively looked at all these paths and tried to increase the flow, and we tried to do that in two ways. So, the first time we picked a certain order of these flows, and then we got a flow of 50, and then we picked another order of these paths, and then we got a solution equal to 55. Now, two things we actually did. One is, in both these instances, we took a path and we increased the total flow or flow in that path if it is possible to increase. So, what we did was, also remember that there were times we said in certain paths we now cannot increase the flow because that path has at least one link which is completely utilized or exhausted. So, only when we could increase the flow in a path, we did it. So, effectively we defined something called a flow augmenting path. So, if there is a path and if that path is made up of arcs, for example, if we consider 1, 2, 5, 7 on the network without these numbers, we said 1, 2, 5, 7 is a path because you have 1 to 2, 2 to 5, 5 to 7. So, it is made up of ij's such that there is an arc from I to j and there is residual capacity that is available. If we leave out this 20, 10 and 25, we said the capacity that is available is 40, 10 and 30, we took the minimum. So, we defined a flow augmenting path as a path comprising of arcs, forward arcs, where there is an arc from I to j and we could move from source to destination or source to sink. So, we defined a flow augmenting path and then we said we found out the maximum capacity that is available in each one of these, and if all of them are positive, the flow can be augmented. So, the flow was equal to minimum of the capacities such that the capacities are strictly positive or greater than 0. So, in each of these methods we identified flow augmenting paths based on this condition. 1, 2, 5, 7 qualified at that time for it. The second one that we observed was that different choice of paths gave us different solutions. So, is there a structure by which we can get the correct order of these paths? That we will see in the next lecture.